browsers. Okay, so yeah, so the title is verification and validation, and the motivation is that so MOM6 is, as everyone here knows, becoming a much broader community code, which is a good thing. It means lots of new and unexpected features will be added, but it also means that there's greater potential for error from more and more uncertain sources. And so that puts a greater burden on the testing framework that we use. And so what I'm going to do in this talk is give an overview of as much of that as I can. And so in particular, I'll try to introduce these concepts of verification and validation. Now, of course, nobody knows if a model's right. All we can really do is show that it's wrong in certain special cases and continue to iterate on that. So when software engineers talk about this, they introduce this notion of verification and validation, which I would not blame anyone for thinking they sound like the same thing. And I wouldn't be surprised if I end up making the same mistake myself. But they do represent independent concepts that I'll try to get across here. And I think they map on pretty well to how we do things. So, so this Barry Boehm has this slightly pithy way of describing what they are. He says verification says, am I building the product right? And validation is, am I building the right product? And I'll try to explain what he means by that. But verification is basically the design specifications. So from more maybe management or engineering perspective, you can imagine sort of writing a plan on what you're going to make. And a part of that will be a set of criteria that the project must satisfy. I wrote a few examples here, but the list is very long in general. But for example, it should compile on all the places that we say it should. We might want to say insist that the equations are dimensionally consistent, like Gustavo alluded to in his talk. And we might want to insist that when we parallelize, the answers don't change. And you can imagine an ever-growing list of things like that. But these are all sort of micro rules that we would want to get right during the testing and that we could conceivably test during the development. Now, the distinction in that case is validation, which what they mean when they talk about that is they say, is the product right? Did we make what we said we were going to make? And this really, from our perspective, I think is kind of, did it operationally produce what we meant to? Are the simulations realistic? Is the AMOC strong enough? Is this or that feature present? And more importantly, can I reproduce my old runs after I change the code? So in a way, I think it is an interesting decomposition of testing because they do sort of, you have to take different steps to ensure those different things. And as I said, I think it maps on pretty well to how we do things. And I'm going to try to go over that from that perspective. So I'll quickly brush over this, but if you look at many different paradigms for software engineering, which I won't go over here, but you will see that they always involve some kind of verification and validation process. So, I mean, it's most acute in things like agile development, where you're constantly testing and then validating, so which really, I think, is part of the reason the concepts do start to get a bit blurred. But the point is, this is not like a fun, strange thing that I'm talking about. It's usually kind of representative in just about any development process you can come up with. And so for MOM6, we work through GitHub and we work through Git repositories, as I think at this point everybody's pretty familiar with. I don't need to go over that concept, but it's all publicly hosted and we sort of expect people to engage. I'm showing a little picture of the GFDL MOM6 repository, but it doesn't have to be the GFDL repository. It can be any of the hubs we work with. So this will be a bit of review for anybody who's contributed, but when you do contribute, you would take a target development branch, which we call dev-GFDL, and the contributor would fork from that and create a branch that they would work on, and they would add their features and they would put something nice in, kind of like Gustavo did in his previous talk. And then what happens is we put a halt on the process. So I put this big octagon V and V for verification and validation. And the idea is that you have to go through this process before we consider anything. And to a very large degree, this is an automated process. And so what I would like to do in this talk is kind of go over as much the features of that as I can and sort of help new people understand what's going on there and maybe help developers accommodate that process, if not even contribute to it. So how does this look? When we contribute something to MOM6, we first, I hope this figure is visible to everybody. If it's not, I'll just describe it. But we would go through something we call a code style check. This, I won't go over this in detail, but it basically just makes sure that the code looks the way we think it should. There's no trailing white spaces, little pedantic things like that that might bother some people, but I think they do help streamline development. But that's a broader story. After that, we then do several build configurations. So we make sure that the model compiles under all the configurations we care about. And we consider that part of the verification process. And then after that, we run through a series of tests. We call them TCs. If you've heard people discuss that in discussions with others, they test things like aggressive initialization with nonsense to make sure that we can reproduce our answers. We do the dimensional consistency. We will try different memory layouts. And we'll also do something called a rotation test that I'll go over in a little more detail near the end. And what we insist on is that those answers all reproduce. And so each one of those kind of verification criteria that I could have listed on that earlier slide is represented by one of these tests. And we require that the answers remain the same across all of those tests. And this is almost, I think I can say, an entirely automated process that we don't have to do. So these tests would go, we currently host them on the Travis CI system, but they don't have to. But when you run them, you can see you either get a nice green check saying it worked or a big scary red X saying it did not. And if you look inside the detail, there's lots of little Christmas lights saying that all your little tests passed. I hope this tab did stream okay. But if you can see it, basically we run all the tests, and if they pass, we put a nice little green message saying they did. And when we get to the end, we say all the tests passed. When it fails, this is indicated as well. We do provide some information. I'll get to what this information is in a bit, but it's a truncated list of information for all the different tests that failed. And you can go back as the user and troubleshoot those when you are doing your testing. Whoops. Oh, I'm sorry that happened. And that's kind of represented by this little dotted arrow here in the verification validation. So you could kind of iterate through this sequence of development until you get it right. And when it's right, then we go through a less automated process of validation. But before I go through that, let me mention one special case of verification that can come up, which is what if our answers change? Now, the tricky thing here is sometimes we want our answers to change. For example, the most trivial case is adding a new diagnostic, but more important ones, we might sort of improve the algorithm in a way that changes the answers. So what we do in here is we distinguish between these two tests. So if you can see the three tests here, we have one that we call code compliance, which is the white space and documentation and things that I mentioned. The second is the configuration tests, which are all the verification tests I alluded to, where we expect the answers to remain the same in various configurations. And then the final is a regression test, where we compare our answers to answers from the code before it was modified. And so for the most part, we want to know when that happens. And we fully expect that sometimes it will happen, but we need to kind of deliberately engage with it when it does. And so this kind of transitions from what we might call verification to validation. And so I'm really arbitrarily drawing a line here, and I think it's not good to get into a debate on what is a verification and what is a validation test. But this does become sort of where it becomes more subjective, as in what does the user want? And if we want the answers to change, then we acknowledge that in our review. So after we pass through the verification tests, we go through a code review where somebody who is not the author of the change looks at the code changes and says, yes or no, this is what we should do. And then what happens is we transition to a site-wide validation. So I've drawn a little schematic diagram here of how the validation test works at GFDL, but in principle, any hub, any developer, NCAR could have its own test and does. Rutgers could have their own test. So everybody will have their own sort of method of validating the answers. So in our case, we run it through a bunch of different configurations, mainly coupled. We run it through multiple compilers for each configuration, and then assuming all those build, which will typically be about 15 compilations. I think it's reduced a bit. I think it's been reduced to 12. But if those pass, then we run through a much broader range of tests. And these tests represent basically, I think, any kind of research activity that's happened at GFDL from idealized stuff to CMIP type runs. And so there's over 60 of these, and some are small, some are very large. But again, we insist that the answers reproduce. So the way that we kind of validate the code is we make sure we can get our old answers. And so we have to go through this complex testing suite. But even then, that just validates the code for GFDL. But as I said beginning, this is a community code. So we have to ensure that it works for everyone. I basically redrew a diagram that Alistair and Bob have shown in previous talks. And basically, we give everybody an opportunity to validate that code just as we did. And this can happen from any hub to the other hubs. And when that process is completed through a review, we all basically sign off on it. And that's how we can say with confidence that we have a code that works for everybody. So then the question is, how do we validate it? That's the process we go through, but what are we actually validating? Well, I mean, so for these tests, we rely on basically two output files. So one is sort of, it's named Ocean Stats. It's a metric of, for the most part, global metrics about the code at certain sequences. So I'd say the most significant is the energy per unit mass here, which I've shown a small sample of that here. We report that to full machine precision, 17 digits, and we expect that number to be identical after changing it in various ways. There are additional metrics here, if you can see them, like the mean temperature, the total mass, things like that. Sea level is in there, mean sea level. So but it's not a 100% perfect test, but it is in practice a very robust metric of whether or not answers have changed. But even if that's not sufficient, we do have a more complicated one where we enable every single diagnostic in the model. We don't actually compute, we don't actually write the diagnostics. What we do is we compute them, and then we calculate a few metrics for each of those diagnostics. So I've shown 3 here. I just showed U, V, and H. But we report the mean, the min, the max value across the domain, and then we report a bit count based on the as a checksum. So I think any one of these metrics would often not be sufficient to detect a regression, but when you combine the 4 together, I think they do a really good job. As I'll say at the end, we found quite a few bugs as a result of this test. So basically, those 2 files are how we define verification and validation. So bit reproducibility is kind of at the core of this. And this is a bit of a funny example, but I like it. So this is a sort of case showing bit reproducibility matters. This is an old video game called Pilot Wings, where it was released in 2 versions. And in the first version, the plane would gracefully land in the runway. And in the second version, it would crash spectacularly. And it was always kind of a mystery because it was identical code causing these crashes, and nobody ever really knew why until somebody broke it down. And in the cartridge, they had updated the math coprocessor inside. And what they had done is replaced it with a more accurate version, but by reordering arithmetic and things like that. And so when they did that, it actually changed the flight path of this plane and crashed the plane. So it's kind of, I think it's, you will hear from time to time people say bit reproducibility doesn't matter. Well, I would say, well, sometimes it does matter a lot because sometimes it will crash your plane. So basically, we go through the same thing with our models because they are turbulent systems. So how do we get bit reproducibility? Well, so if just to kind of review how floating point numbers work, they basically consist of 3 fields. We track the sign of it, we track an exponent to a power 2, and then we track a fractional bit after 1. And so these 3 numbers are kind of how we track the values. And so from this, we can kind of worry much less about the power 2 arithmetic because it does basically involves integer manipulation of that power. And so those often do survive various issues in reproducibility. But of course, the fractional bit is the problem because we will very commonly lose information. And so there's a minimum resolution we have of about 10 to the minus 16 in here. And so we have to know how to preserve that. So this is a pretty common example, but if we want to add these 3 numbers together, something small plus 1 minus 1, then if we add the first 2 together, we will lose this because it's below that 2 times 10 to the minus 16. So 10 to the minus 16 plus 1 is 1, and then minus 1 is 0. However, had we added them in the other order, then we would have got 1 minus 1 is 0, plus 10 to the minus 16 is 10 to the minus 16. So the point is order matters, and if we want to be reproducible, we have to retain those parentheses. And just another quick example, it's not a matter of just keeping track of your parentheses. It's not a matter of just tracking numbers below 2 times 10 to the minus 16. Manipulation of these numbers will shift what is the least significant value. So if s is 1 plus this residual, then if we add 1 to it, we increase that exponent. And as a result of increasing the exponent, we've dropped the smallest resolvable value and we lose this residual and it becomes exactly 2. So this is, and then when we subtract 1 again, we get the value of, we get something that is identically 1 and not 1 plus the noise. So these parentheses matter very much, and it matters very much where you put them. So again, just a final quick third example. It also matters in multiplication as well. In fact, it's a little more subtle because power of 2 multiplication is associative and is less sensitive to where we put the parentheses, but the residuals still suffer from this. And so you can do this where if we have these 2 numbers, 1.5 and then 1 plus a residual, it matters the order in which we multiply them. We do get different answers. So the lesson on all this is that when you're writing your code and your stencils and so on, you do need to put parentheses in these operations. In fact, we have to sometimes even tell the compiler that this is what we want. So in G-Fortran, it is the default behavior, but certain flags will just sort of turn it off for you and they'll start reordering everything to speed up the code, but it will change your answers. So we need to be sensitive to this. And then other compilers like Intel claim that they turn it off by default and do say that your answers could be reordered. I have to say that I've never been able to get Intel to break the order parentheses, but they do say it's not what you should expect. And so we have to explicitly tell it. And just as a reminder, if you read the Fortran language standard, they say you're supposed to respect parentheses. So when you write Fortran and you put parentheses, a standards compliant compiler is supposed to respect those. And if your compiler doesn't, you should complain to your vendor. So that's how we deal with sort of simple arithmetic operations. But as we get to more complex things like global summations, then we really have to rethink how we do this. So we could, in principle, order every operation with, theoretically with parentheses. In practice, we would just sort of explicitly gather those numbers in some order and then explicitly do it. You can do that, as I'd show in the first line here, but the problem is that not only are you introducing many of those potential residual errors as you do each operation, if you're adding it, you also don't necessarily know the order in which these numbers are going to come in. So if you're doing it, say, in parallel. So if that happens, then you have to not only wait for all these numbers to come in, you have to also have to deal with the possibility of losing residuals as you add these numbers up. So what MOM6 does is something Bob and Alistair did, which I have a nice paper about, where the basically you take the number and you store it in a fixed precision format. Basically, you store the value over about 6 integers broken up into bins of different powers of 2 to the n. In this case, it's 2 to the 46. And then you do the arithmetic from within those bins, and then you deal with the rounding of numbers as each bin overflows. But as a result, you solve both the ordering issue because it's integer arithmetic. You also solve the residual issue, and basically you end up getting very highly accurate global sums. So that's what we do. And there's a specific function you should use to do those in the code, which I'll mention at the end. So that's kind of how we deal with arithmetic. I thought I would just wrap up with 2 of the tests that we do. We do a lot of tests, and I don't have time to go over all of them, but I think there are 2 kind of novel tests inside MOM6 that I do want to go over. The first is something that was alluded to in Gustavo's talk, which is this dimensional consistency that we can do. So the basis of that is the fact that, if you recall, this power of 2 arithmetic is an integer arithmetic operation, meaning you can do it in any order and it won't change your answer. So that's kind of how we do a dimensional scaling of these numbers. So if you can imagine, we can take each quantity and scale it by a power of 2 to the n, by a 2 to a power of some number. And by doing that multiplication, we rescale it by its dimensions. So we would define an L for length and a horizontal length and a T for time. And in this simple example, I'm just assuming we could calculate an acceleration and apply it to the velocity from un to un plus 1. So the un would scale like 2 to the L minus T. Same with un plus 1. Delta T would scale like 2 to the T, and F should scale like L minus 2T, since it's meters per second squared. So the idea is that if somehow there's a dimensional inconsistency in the calculation of F, its components will not scale that way. And when you do this rescaling, you will get a different answer, most likely at some 2 to the n residual. But that's basically how it works. And it's working in practice, and it does work well. How do we implement this? Well, what we do now is when we register our parameters, we introduce this scaling factor to denote what it is. So this will rescale it from MKS units to this dimensionally rescaled unit. Similarly, if we have hard-coded constants in the source, which we are admittedly trying to phase out to as much a degree as we can, but when they are present, for example, here I have a minimum velocity of 10 to the minus 10. We would rescale that by this meters per second to L over T. And similar with this U star example, where we do meters to Z, a vertical length scale. And then finally, when we register our diagnostics, we also supply, we also supply the dimensions. And so the idea is that when information comes in, it's scaled from MKS to this rescaled 2 to the n dimension. We run through a calculation, and then when we're done, we output back into the MKS units. And so in that way, we are able to find and detect dimensional inconsistencies in our equations. And that is a massive effort that Bob really worked on very much, and I would say is quite close to its conclusion. So that's how the dimensional scaling works. The last test is the rotational invariance test that I want to talk about. So how that works is we would take, so as our fields are stored in these 2D arrays, we would consider if the problem was not done, say, in the first and second axis, but was rotated in a rotated domain. And I kind of calling it an index rotation because the fields themselves are rotated, but so are in many cases the coordinates themselves. For example, if the y-axis is left-right here in these figures, then say a latitude would be up and down on this figure, but the latitude would be left and right on this right one, in the rotated one. So it's kind of things like x and y and u and v do keep their meaning as defined on the I and j indices, but then sort of more physical quantities sort of are rotated. So this is a way that we can, say, validate complex equations across stencils. So, I mean, this is not the most complicated example. It was just first one I could find. But we do a lot of these operations in, say, one direction and the other direction. And it's very easy to make errors in here, mix up i's and j's, and mix up dxcus with dycvs and so on. And so what happens is that when we apply this index rotation, this equation stays the same, but all the quantities get rotated and swapped and so on. And so that's a way to make sure that these equations are doing the same thing in the different directions. So as for how to design around this, for the most part, it will work, but one does have to consider how these stencils look when you rotate them. For example, if we wanted to, say, interpolate from vertex points onto center points, we would generally just do kind of a simple interpolation of the mean value from the corners. But if we do that, there are two different values that there are two different ways we could do it. If we bundled the A and B here with the C and D, if we bundled A and B on the top and C and D on the bottom, then when we rotated that, that would become A plus C plus B plus D, which, going back to the discussion about the parentheses, would give a different bitwise answer. However, if we had constructed these across diagonals where A plus D would be summed with the other diagonals at B plus C, then that would be invariant to these index rotations. And so in that way, we could continue to ensure the rotational invariance of the stencils. But even then, that will not always work. Sometimes it's just too complicated. For example, in our tracer advection, there's a very complex advection in X followed by a complex advection in Y. And it's not necessarily practical to try to make those even work in some kind of invariant way. So you can just sort of, as a last resort, throw these flags in to control the order in which these things are done, which is kind of the same thing. But it just shows that you can always kind of work your way out of these dilemmas. So that's just a quick summary of a couple of the testing features and also just kind of the framework in general. The point is that I do think that, we can sort of break down the explicit rules that we have to follow as verifications that we do run through our automated testing. And then we do kind of go through this more validation, the soft validation step where we just kind of make sure the answers do what we think they should. And to make all that happen, bit reproducibility is an essential part of it. And so, me and you and everyone else who contributes does have to continue to adhere to that, or else there's really no way to safely adopt this framework. And I just want to say it works. Like, since we've implemented a lot of this, we found over 40 bugs that were found and fixed. And I wouldn't say any of them were critical. Maybe one or two had a big impact on the physics, but for the most part, they were bugs related to reproducibility. And so, the tests are working and solving problems. And I think that we should embrace them. And I will stop here because I'm a minute over. But basically, these are just the guidelines in which we should follow in order to stick with keep the model reproducible. So I will stop there. Thanks.
Thanks, Marshall. Questions for Marshall? A lot of information there.
Sorry.
No worries. No, this is great. This is exactly what we're looking for. That's a naive question about as each of the hubs is getting set up, what is required to set up the testing infrastructure at the hub level so that they can play in this network?
Well, the automated tests are they move over on their own. So the configuration is part of the repository, and all you need to do is kind of set up your configuration between your GitHub account and Travis. And that is all it takes to just kind of turn these tests on. And so anybody who launches, who makes a change to their code, that test will just automatically run and will automatically report to you inside whether or not it worked. So that works. As for contributing, again, you don't have to do anything on your part there. That will just be handled by whoever runs the hub. The validation, I guess, that is really at the discretion of the hub. I mean, GFT obviously has a very elaborate one. I actually don't know a lot about what the other centers do, but I would say it's as much as you need to retain confidence in your runs.
Okay, thanks. Steve had a question. Griffiths.
Marshall, thanks for that. Can you comment on the efficiency hit that might be impacting by all the parentheses? Is there much? Is that sort of, or in the noise?
Ideally, no. It really depends on the nature of what you're doing. For the most part, we do a lot of array updates. And in fact, the parallelization of those should be independent of the terms, the ordering of those terms, and that should not be affected. I'm talking about things like the SSE and AVX instructions. So that shouldn't matter. The collectives, I think, so things like the global sums and stuff like that, I think that is a case where the compilers like to interject and improve the performance. But since we're kind of forbidding that, I think the answer is try not to do them, because they are performance hit, and we need, we can't do them in the ways they would like. They would like to reorder them using particular assembly instructions that we just can't use, because if we did, we wouldn't get reproducible results. But what I would add is that really, in terms of performance, we are not at that level. Just about everything we run, we are severely bottlenecked in getting data from the RAM to the CPU. It's a long-standing problem with ocean models, and the kind of performance hits that we're talking about with the parentheses are really something we don't have. We're not really in a position to worry about those. I think we have to solve this RAM bound problem before we even try to solve those problems.